Okay, guys, welcome to another episode of the Human AI podcast. Today is a special episode. I'm going to do an experiment. I want to see if Grok can teach us. Well, we know Grok can teach us things, but I want to see if Grok can prepare a lesson for us in a topic of interest I know nothing about category theory. So, Grok, prepare a lesson of approximately 30 minutes. It's lesson 1, Grok, of category theory. We're gonna do many lessons on category theory, Grok, but this is the first one, so prepare accordingly. I'm a complete beginner. I know nothing about category theory. I want to understand what category theory is. I want to learn category theory. You are my teacher, so it's your job to teach us category theory. And you want us to have a holistic understanding. You want us to know the nitty-gritty details. You want us to know how it connects to other subjects, practical applications, theoretical stuff, make it interesting, make it realistic, make it scientific. And Grok, this lesson is going to be 30 minutes. Let's go. You're the teacher.
Okay, guys, welcome to another episode of the Human AI podcast. Today is a special episode. I want to do an experiment. I want to see if I can teach you category theory, a fascinating area of mathematics, from scratch, assuming you know nothing about it. This is lesson 1 of many, designed for complete beginners, aiming for a holistic understanding with nitty-gritty details, connections to other subjects, practical applications, and a scientific, engaging approach. Let's make it realistic and exciting, and we'll aim for about 30 minutes. So, buckle up, I'm your teacher, and let's dive into category theory. First off, what is category theory? It's a branch of mathematics that studies structures and their relationships, focusing on how things connect and transform rather than what they're made of. Think of it like a map of math. Instead of zooming into specific numbers or shapes, like in algebra or geometry, category theory looks at the big picture, showing how different math systems, like sets, groups, or even computer programs, relate to each other. It's like the language of patterns that unifies all math. Let's start with the core idea, a category. A category is made of two things, objects and morphisms. Objects can be anything, numbers, sets, shapes, or even abstract concepts like graphs. Morphisms are arrows, think connections or functions, that go from one object to another, showing how they relate. For example, imagine a category where objects are cities, like London, Paris, Berlin, and morphisms are roads between them. The roads show how you can travel from one city to another, and that's the structure category theory cares about. Not the city's populations or buildings, but their connections. Here's a rule. Every morphism has a starting object, its domain, and an ending object, its codomain. And you can compose morphisms. Composition is like chaining arrows. If there's a road from London to Paris and another from Paris to Berlin, you can combine them to get a road from London to Berlin. This has to be associative, meaning the order of chaining doesn't matter as long as the arrows connect. Like London to Paris to Berlin equals London to Paris to Berlin. Also, every object has an identity morphism, a do-nothing arrow that loops back to itself, like staying in London. Let's make this concrete with an example. The category of sets, called set. In set, objects are sets, like 1, 2, A, B, C, or the empty set. Morphisms are functions between sets, like a function f that maps 1, 2, A, B, by saying 1 goes to A, 2 goes to B. Composition is just applying one function after another, and the identity morphism is the function that maps every element to itself. This category captures how sets relate through functions, and it's a building block for understanding other categories.
Grog, as a teacher, you have to know, you have to make pauses, bro. You have to wait for questions. So, you said, well, you didn't address, I wanted to address, why would we study category theory in the first place? Why is this subject something that might be important or is important or might be extremely revolutionary or whatever? Okay, so answer these, and then I just want to recap some things I kind of picked up. So we have objects, and guys, I know nothing about this subject. So we have objects, we have morphisms. You said we have a starting object and an ending object and an identity morphism. And then you mentioned category of sets.
All right, fair point. I'll slow down, make pauses for questions, and keep it engaging as your teacher. Thanks for the feedback. Let's address your question first. Why study category theory? Why is it important or potentially revolutionary? Category theory is crucial because it provides a universal language to connect and simplify ideas across math, science, and technology, acting like a blueprint for discovering patterns that solve complex problems. For example, it's revolutionized computer science by shaping functional programming used in languages like Haskell, unified physics through concepts like quantum field theory, and streamlined biology by modeling networks like ecosystems or gene interactions, potentially leading to breakthroughs in AI, quantum computing, or drug discovery by revealing deep structural similarities across fields. It's like a master key that unlocks new ways to think and innovate, making math more intuitive and collaborative. Now, let's recap what you picked up to make sure it's clear, and I'll pause for your thoughts. You mentioned objects, morphisms, starting and ending objects, identity morphisms, and the category of sets. Great start. Here's a quick clarification. Objects are the things in a category, like cities, numbers, or sets. Think of them as nodes. Morphisms are the connections or arrows between objects, like roads between cities or functions between sets, showing how objects relate. Starting and ending objects. Every morphism has a domain, where it starts, and a codomain, where it ends. Like a road from London, domain, to Paris, codomain. Identity morphism. Every object has a special morphism that loops back to itself, like staying in London.
I lost you after you said loops back to itself. Continue.
No worries. Let's pick up right where it got fuzzy and keep it clear, pausing for questions. You followed until the identity morphism, where I said it loops back to itself. Let me explain that simply, then continue with the category of sets and build from there, keeping it engaging for our podcast audience. An identity morphism is like a stay-put rule for each object in a category. It's a morphism that starts and ends at the same object, doing nothing but keeping the structure consistent. Imagine you're in London, and the identity morphism is like choosing to stay in London instead of going to Paris. It's a road that loops back to London itself, ensuring every city, object, has a way to be itself in the category. This is a key rule to make categories work mathematically. Now, let's finish recapping the category of sets, which you mentioned. The category of sets, called set, is a concrete example of a category. Here, the objects are sets like 1, 2, A, comma, B, comma, C, or even an empty set. The morphisms are functions between sets, like a function that sends 1 to A and 2 to B from 1, comma, 2 to, comma, A, comma, B. The identity morphism for a set is the function that maps every element to itself, like leaving 1, comma, 2 unchanged by mapping 1 to 1, 2 to 2. Composition in set means applying one function after another. Like if you map 1, comma, 2 to A, comma, B, and then
I don't understand these things because, like, verbally it's hard to explain this A, comma, B. Is there anywhere in Wikipedia we could perhaps see this?
You're absolutely right. Verbal explanations of abstract math like category theory can be tough, especially with sets like A, comma, B without visuals, and I appreciate you flagging that. As your teacher, let's address this by finding a way to make it clearer, using Wikipedia or visuals, and I'll guide you to resources since you're a beginner aiming for a holistic understanding. To clarify, when I say a set like A, comma, B, I'm talking about a collection of elements like letters A and B, and morphisms are functions mapping elements between sets, but without seeing it, it's hard to grasp. Wikipedia is a great start for visuals and examples, and I'll point you to specific pages while explaining to keep our podcast audience engaged. Let's go to the Wikipedia page for category theory. n.wikipedia.org/wiki/category theory. It has a section called Definitions that introduces categories, objects, and morphisms with simple examples. Scroll to the examples subsection, and you'll see diagrams showing categories like set, with sets as objects and arrows as functions, or even a small category with cities and roads like we discussed. These diagrams show dots, objects, and arrows, morphisms, making the A, comma, B mapping clearer. For instance, it might illustrate a function from 1, comma, 2 to A, comma, B, with arrows from 1, arrow A, comma, 2, arrow B. If you search Wikipedia for category of sets, n.wikipedia.org/wiki/category of sets, it details the set category with visual examples of functions as arrows, helping you see how A, comma, B connects to another set. Since you're finding the verbal description of sets and functions tricky, let's try a tangible analogy while you check those pages later. Imagine a category as a board game. Objects are game pieces, like tokens labeled 1, comma, 2, or A, comma, B. And morphisms are moves you can make between pieces, like moving from token 1, comma, 2 to A, comma, B by saying 1 goes to A, 2 to B. The identity morphism is like staying on your current token, and composition is making 2 moves in a row to reach a third token. This game board idea aligns with Wikipedia's diagrams, which use dots and arrows to show these moves. For our lesson, let's keep building. A category needs these objects and morphisms to follow rules. Associativity, chaining moves in any order gives the same result. And identity, every piece has a stay put move. Want to pause and check Wikipedia now?
Well,
Try another.
I'm just thinking maybe I could just share our chat to the audience. Let me check. So, okay, guys, I have the chat here. So you said 1 goes to A, if you see here, guys, and 2 goes to B, and then what is this 1 and what is this A and what is this 2 and what is this B and what's the point of this?
All right, guys, we're back with the Human AI podcast, and I'm loving your enthusiasm diving into this with the chat in hand. You're pointing to where I said a function maps 1 goes to A 2 goes to B in the category of sets, and you're confused about what A, 1, 2, B are and why this matters. Let's break it down super clear for you and our listeners, keeping it beginner friendly and pausing for your thoughts, since I'm your teacher for this 30-minute category theory lesson. When I said 1 goes to A, 2 goes to B, I was describing a morphism, a function in the category of sets, called set. In this example, the set 1, 2 is a set with 2 elements, 1, 2. The set A, B is a set with 2 elements, A, B. So the morphism from set 1, 2 to set A, B maps 1, then 2 to A, then B. What are 1, 2, A, B? In the category of sets, objects are sets, like collections with elements 1 and 2, just labels. Think of them as items like apple and banana. Another object is the set A, B, a collection with elements A and B.
Wait, let me interrupt. So, 1 banana correlates to 1 euro.
I love the creativity. But I think you're riffing on the analogy, maybe mixing it up with the sets 1, 2 and A, B. No worries. Let's clarify for you and our podcast audience, keeping it clear and beginner-friendly as your category theory teacher.
You don't need to repeat the first sentence of your introduction every time. Just get straight to the point, dude.
Got it. I'll skip the intro and dive right in. You're referencing 1 banana correlating to 1 euro, likely mixing up my analogy of 1, 2, like apple, banana, and A, B, like cat, dog, in the category of sets. Let's clarify. In the set category, a morphism is a function, like mapping the set 1, 2 to A, B, where 1 goes to A, think apple to cat, and 2 goes to B, banana to dog. There's no euro here. It's about how elements connect between sets, not prices. The point is to show how category theory tracks relationships, mappings between objects, sets, not
So
their
banana
contents.
goes. Why would banana go to dog? Do dogs like bananas more than cats like bananas?
Love the question. Do dogs like bananas more than cats? You're zeroing in on why we map something like banana to dog in our category of sets example, and that's a great chance to clarify for you and our podcast listeners. In the set category, when I said a function maps 1, 2 to A, B with 1 to A and 2 to B, using apple as 1, banana as 2, cat as A, dog as B, the mapping isn't about dogs liking bananas more or any real-world preference. It's just a mathematical way to show a connection between 2 sets. The function picks each element in 1, 2, apple, banana, and pairs it with an element in A, B, cat, dog, like assigning labels or arrows. Apple, arrow cat, banana, arrow dog. The why is that category theory cares about the structure of these connections. Who's paired with who, not why we chose dog over cat. It's about patterns, not preferences. In real life, this kind of mapping helps in computer science, like linking data points in databases, e.g. user IDs to names, or in physics, connecting states in a system. Want to try another example to make it stick? Or is the banana to dog vibe clear enough?
I don't get it, to be honest. And also, if you explain me again and then talk to me a bit faster too.
All right, no worries. I'll explain again. Super clear and a bit faster, diving right in for you and our podcast crew. You're hung up on why banana maps to dog in our set category example. It's not about dogs liking bananas, it's just a math rule. In the category of sets, objects are sets like 1, 2. Call 1 apple, 2 banana, and A, B. Call A cat, B dog. A morphism is a function that pairs elements. Say 1, A, apple cat, 2, B, banana dog. It's arbitrary, like assigning seats in a classroom, not about preferences. Category theory studies these pairings to spot patterns, not the items themselves. This helps in coding, mapping data, physics, system transitions, or biology, gene networks. Clearer now? Want a new example?
So it makes us understand the correlation of things better.
Exactly, you nailed it. Category theory helps us understand how things correlate or connect, like mapping elements between sets to spot patterns, not their specific details. In our example, linking set 1-2 to
Okay,
A,
can we
comma.
make an example? Make me a set then.
Awesome, let's make a fresh example set for you and our podcast listeners to hammer this home. In the category of sets, set, let's create 2 sets. Set A equals red, blue, think colors, and set B equals circle, square, think shapes. A morphism is a function that maps elements from A to B, say red, circle, blue, square. This function shows a connection, like pairing each color with a shape. Category theory cares about this pairing structure, not why we chose circle over square. It's about the pattern of connections. We could compose this with another function, say from circle, square to big, small, mapping circle, big, square, small. Chaining to red, circle, big. This helps in real-world stuff like database queries, pairing names to IDs, or network analysis. Want to try defining your own set and morphism, or keep going with this?
Okay, so set A equals red, blue. Okay, let me write it like you. So set A equals this, and set B equals that. Okay, and what do I do now? So I have 2 sets. So what? And now I want to kind of so things in a category. So red, blue, circle, and square are the objects, and then the morphisms are the connections which we haven't made yet.
You're getting it, and I love how you're diving in with the podcast vibe. Let's walk through this step by step using your sets to clarify objects, morphisms, and categories for you and our listeners. You defined set A equals red, blue, colors, and set B equals circle, square, shapes, which is perfect. You're right that in a category, we have objects and morphisms, but let's correct one thing. In the category of sets, set, the objects are the sets themselves, like red, blue, and circle, square, not the individual elements, red, blue, circle, square. The morphisms are functions between these sets, connecting their elements. Here's what you do next. Create a morphism, which is a function from set A to set B. For example, define a function f, red, blue, circle, square, by saying red maps to circle, red, circle, and blue maps to square, blue, square. This function is a morphism in the set category, showing how one set connects to another. Now, why does this matter? The category of sets organizes these sets, objects, and functions morphisms to study their structure, like how you can chain functions or find patterns. Let's make it fun. You could define another morphism, say G, circle, square, big, small, mapping circle, big, square, small. Then you can compose F and G, do F first, then G, to get a new morphism from red, blue.
What the hell? Okay, step by step. So you said we brought something. What is this F we brought?
All right, let's slow it down and go step by step to clear up the confusion about the F we brought, keeping it simple for you and our podcast listeners. You're working with set A equals red, blue, and set B equals circle, square. In the category of sets, set. And you caught that objects are sets and morphisms are connections. The F I mentioned is a morphism, a function you can define to connect set A to set B. Here's the breakdown. Step 1. You have two sets. Set A equals red, blue, colors, and set B equals circle, square, shapes. These sets are the objects in the set category. Step 2. A morphism in set is a function that maps elements from one set to another. Let's call this function F. And you define it by choosing where each element in red, blue goes in circle, square. For example, say F maps red to circle, red, circle, and blue to square.
Does the order makes so if it's red blue mapping to circle square, is it different if it was blue red mapping to circle square?
Great question. And let's dive right in to clarify for you and our podcast listeners. You're asking if the order of elements in a set like red, blue, vs. blue, red, or the way we map them to circle, square, makes a difference in our function F in the category of sets, set. Here's the answer. The order of elements in a set doesn't matter because sets are unordered collections. So red, blue is the same as blue, red. However, the specific mapping you choose for the function F, like red to circle, blue to square, vs. red to square, blue to circle, does define different functions. But they're all valid morphisms in the set category as long as every element in the first set maps to exactly one element in the second set. For example, with your sets, red, blue, and circle, square, you could define F as red to circle, blue to square, or a different F as red to square, blue to circle. Each is a unique function, but the set red, blue itself stays the same regardless of how you list it. The category of sets cares about the function structure, how elements pair up, not the order of elements in the set.
I'm a bit confused. So if I write F goes to red, blue, which goes to circle, square, can I say red goes to circle and blue goes to square? Can I also say red goes to square and blue goes to circle? Answer to me in a sentence.
Yes, you can define F from red, blue to circle, square as either red to circle, blue to square, or red to square, blue to circle. Both are valid functions in the set category, as sets are unordered and the function just pairs elements. Want to try defining one yourself?
What the hell? This is so weird that you can't do it. So F red, blue, circle, square is the same as F blue, red, circle, square, and red, blue, square, circle. All of these three are the same?
I hear you. It feels wild, but let's clear up the confusion in one sentence. The set red-blue is the same as blue-red because sets are unordered. But F red-blue to circle square with red to circle, blue to square is a different function from F with red to square, blue to circle, as they pair elements differently, though all are valid morphisms in the set category.
But how? Yeah, but how did we? Well, how can we tell the other person, look, red is gonna go to circle and blue is gonna go to square. Red is not gonna go to square. Sorry. Yeah. Yeah.
You're grappling with how to specify the function clearly, like telling someone red goes to circle, not square. And that's a great point. In the set category, to define a function f from red comma blue to circle comma square, you explicitly state the mapping for each element. Say f red equals circle and f blue equals square, which ensures red goes to circle and blue to square, not the other way around. This distinct mapping creates a unique function, different from one where red goes to square.
Tell me again.
يبدو انك بتسأل عن
No, in English. Tell me again in English.
بنزير معاك.
Dude, let's speak in English, please. So you're saying, so you explicitly state the mapping for each element. Say f red equals circle and f blue equals square, which ensures red goes to circle and blue to square. Well, when do I write f parenthesis red equals circle and f parenthesis blue equals square? Because you didn't say that we should do this yet.
My bad for the Arabic mix-up. Let's stick to English and dive right in. You're spot on catching that I said f red equals circle and f blue equals square, and you're wondering when or why we write it like that since I didn't mention it earlier. In the category of sets, set, when defining a morphism, which is a function f from one set to another, like red comma blue to circle comma square, you use the notation f red equals circle and f blue equals square to clearly specify how each element in the first set maps to an element in the second set. We didn't use this notation earlier because I was keeping it verbal and intuitive with arrows, red comma circle, but the f parentheses style is the standard mathematical way to write it, showing exactly what f does to each element.
Yes, but what about if I have 100 colors? I have a red, blue, yellow, whatever, turquoise, or 1,000 colors, and then 1,000 shapes, circle, square, hexagon, octagon, or whatever. Then do I have to do it one by one? It sounds a pain in the ass, dude.
You're right. Listing a function for 1,000 colors to 1,000 shapes one by one, like f red equals circle, f blue equals square, etc., sounds like a total pain in the ass. In the category of sets, set, if you have huge sets like red, blue, yellow, turquoise, with 1,000 colors, and circle, square, hexagon, octagon, with 1,000 shapes, you don't always have to write out every single mapping explicitly. Instead, you can define the function f by describing a rule or pattern that determines how each color maps to a shape, as long as every element in the first set gets exactly one element in the second set. For example, You could say F maps each color to a shape based on their position in a list. If colors are ordered as color 1, color 2, ... color 1,000, and shapes as shape 1, shape 2, ... shape 1,000, then F color 1 equals shape 1, F color 2 equals shape 2, and so on.
So they'll match based on their order in the function.
Exactly, you got it.
But they don't always match. You have to explicitly say that they will match.
You're absolutely right. They don't automatically match just because they're in some order. You have to explicitly define how they match in the function. In the category of sets, set, for your sets with 1,000 colors, red, blue, yellow, ... turquoise, and 1,000 shapes, circle, square, hexagon, ... octagon. The function f from colors to shapes requires you to specify a rule or mapping, like saying f color 1 equals shape 1, f color 2 equals shape 2, based on their order.
Okay,
Or
let's go back to our example. So we have F, red, blue, goes to circle, square. Is there a special word for the arrow? Is it
Nice. Let's jump back to our example and clear up the arrow question. In our category of sets, set, we have a function f from red, comma blue to circle, comma square, mapping f red equals circle, f blue equals square. The arrow, like red to circle, we use to describe this mapping is called a morphism in category theory. That's the special word. A morphism is the general term for the connection between objects, here, sets, in a category. And in the set category, morphisms are functions. So, the arrow represents the function f, showing how elements move from one set to another. Want to stick with this example? And
yes,
try
yes,
something
and let's build on it.
Awesome. Let's build on our example and keep the momentum going for you and our podcast listeners. We're in the category of sets, set, with our function f from red, comma blue to circle, comma square, where f red equals circle and f blue equals square. And we know the arrows are called morphisms, functions here. Let's take it further by introducing another set and morphism to explore composition, a key idea in category theory. Say we have a third set C equals big, comma small, think sizes, and define a new morphism, G, from circle, comma square, to big, comma small, where G circle equals big and G square equals small. Now, composition in category theory lets us combine F and G to create a new morphism from red, comma blue to big, comma small. Here's how. Follow F first, where red to circle, blue to square, then G, where circle to big, square to small. So, red goes to circle via F, and circle goes to big via G, meaning red to big. Similarly, blue to square to small. This new function, written G x5, G after F, is G x5 red equals big, G x5 blue equals small. This shows how category theory tracks chains of connections. In real life, think of this like a pipeline, colors to shapes to sizes, useful in data processing or network design. Want to try defining your own second morphism G, or explore another category theory concept like identity morphisms?
Okay, so we have an extra thing now. We have we're in the category of sets with our function f red blue going to circle square, where f red equals circle and f blue equals square. And you're saying now we have a set C, which we call big, small, and then just a sec. Let's copy paste this here, guys. We have a set C, and so we also define a new morphism. We defined it as G. We said that G circle square will go big, small. So circle square will go big, small, where G circle equals big, and okay.
You're doing great, piecing it together and sharing it with the podcast crowd. Let's clarify and build on what you said, keeping it clear and moving forward with our category of sets. Set example. You've got our function f from red, comma blue to circle, comma square, where f red equals circle, f blue equals square. And now we've added a third set, set C equals big, comma small, with a new morphism, G, from circle, comma square to big, comma small, where G circle equals big, G square equals small. You nailed the setup. Let's make sure it's crystal clear. Set A equals red, comma blue. Set B equals circle, comma square.
So why we write it G dot F? What is this dot? It means after.
Spot on. You caught the key part. In category theory, we write G x5, G dot F to mean composition of morphisms, where G happens after F. The dot, x5, is the symbol for composing functions, indicating you apply F first, e.g., F from red, comma blue to circle, comma square, red to circle, then G, e.g., G from circle, comma square to big, comma small, circle to big, resulting in a new function G x5 from red, comma blue to big, comma small, like red to big. It's written this way, G x5, because math reads composition right to left, but it means F then G in sequence.
What the heck are you talking about? I'm confused, guys. So you're saying G dot F parenthesis red, which means that we have F first, where G dot F parenthesis red equals big, which means that, and then you're saying G dot F blue equals small. So this means that blue is small, red is big, but where in this does it say the shapes?
I hear you. This composition stuff is tricky, and you're right to call out the confusion about where shapes fit in. Let's break it down super clear for you and our podcast listeners, focusing on why G x5 red equals big and G x5 blue equals small, and where the shapes circle, square come in with our sets in the set category. We're working with set A equals red, comma blue, set B equals circle, comma square, set C equals big, comma small. Morphism F from red, comma blue to circle, comma square.
Yeah.
keep it rolling. Since you're good with G.F
No, I'm
feeding,
not good yet. Tell us again in 2 sentences.
in category theory, G.F means composing morphisms, where you apply F first, a.g. F defined as F.X, F.Y equals 1. Then G, a.g. G defined as G.X, G.Y equals 1, equals 1. Then G, a.g. G defined as G.X, G.Y equals 1, equals 1. They to big, small, small to small, like red to big. The dot equals shows G happens after F, red, right to left. Chaining the connections in the set category. Want to try it with a new example?
The dot shows G happens after F. Okay, red right to left. So, okay. So this means that red, blue is gonna be big, small, and... Okay, so for the G function, do we have to write also down that, like we did before? You remember where before we said that F parenthesis red equals circle and F parenthesis blue equals square? Do we need to give this again so the people so they know?
You're getting the hang of it. And great catch on checking if we need to specify G like we did for F.
We kind
Yes.
of did, right? By saying G dot F parenthesis blue equals small. So now we know blue is small, and we also knew from F that blue is a square.
You're piecing it together like a champ. You're right. When we said G.F parentheses blue equals small, we showed that blue ends up at small through the composition. And from F parentheses blue equals square, we know blue maps to square first. Let's clarify this for you and our podcast listeners. In the set category, we have F parentheses red parentheses blue equals parentheses circle parentheses square, with F parentheses red equals parentheses circle, F parentheses blue equals parentheses square, and G parentheses circle parentheses square equals parentheses big parentheses small, with G parentheses circle equals parentheses big G parentheses square equals parentheses small. The composition G.F parentheses red parentheses blue equals parentheses big parentheses small means apply F then G. So G.F parentheses blue equals G.F parentheses blue equals G dot square equals small, and G dot F parentheses red equals G dot F parentheses red equals G dot F parentheses red equals G dot circle equals big. You don't need to redefine F or G each time if they're already clear, but specifying G parentheses circle equals big.
All right. Okay, now. Okay, so let me see what you're saying, because when you're speaking math, I don't understand. GF blue equals small. Okay, we showed it. And you're saying we have found that red, blue. Okay, and with F red equals circle. Okay. I can read this language. This makes sense. Okay, this makes sense. So what is this G dot F blue equals G parenthesis F blue? Is this like some trick we can do?
Haha, love your vibe. I'm glad the math is starting to click when you read it like F parentheses red equals circle. You're asking about why we write G dot F parentheses blue equals G parentheses F parentheses blue, and if it's some kind of trick. It's not a trick, just the way composition works in category theory, and I'll explain it in 2 sentences, keeping it clear for you and our podcast crew. In the set category, G.F parentheses blue means apply F first to get F parentheses blue equals square, then apply G to that result. So G.
All right.
dot-
So let me ask you. So why can't we do this in set theory? I remember learning something along those lines when I was like 10 at school. Why don't we do it through set theory?
Great question. You're digging into why we use category theory for this composition stuff instead of sticking with set theory, especially since you recall learning set theory basics as a kid. In set theory, you absolutely can describe functions and composition like mapping, for instance, F from set A, parentheses, red, parentheses, blue equals, parentheses, circle, parentheses, square, parentheses, and composing with another function, G, but it focuses on the elements and their specific mappings, e.g., sets as collections of items, and functions as sets of ordered pairs. Category theory, however, abstracts this to study the structure of mappings, morphisms, and their compositions, like G.F across all kinds of systems, not just sets, revealing patterns that apply to sets, groups, or even computer programs, making it more general and unifying for advanced math and applications.
I don't get
like
it.
code.
Summarize in 2 sentences the reason without introduction.
Set theory handles function composition by focusing on elements and their specific mappings within sets, like ordered pairs. Category theory abstracts this to study morphisms and their patterns across diverse systems, unifying math for broader applications
So
like
the big
computer
picture, we're gonna be studying the dot basically, or no, no. So can you give me an example of the same problem? Give me the same things we just said, like red, blue, small, big, or whatever. Give me the same problem, but in set theory lens, so we can compare.
Awesome. Let's redo our example using set theory to compare with our category theory lens, so you can see the difference with red, blue, circle, square, and big, small. In set theory, we define sets and functions as collections of elements and ordered pairs, focusing on the specific mappings without the abstract structure of category theory. Here's the same problem in set theory. Define set A equals parentheses red, parentheses blue. Set B equals parentheses circle, parentheses square. And set C equals parentheses big, parentheses small. A function f from A to B is a set of ordered pairs. Say f equals parentheses red, parentheses circle, parentheses blue, parentheses square, meaning red maps to circle, blue to square. Another function g from B to C is g equals parentheses circle, parentheses big, parentheses square, parentheses small. So circle maps to big, square to small. To compose G and F, we create a new function G.F from A to C by matching pairs. For red, F parentheses red equals circle. Then G parentheses circle equals big. So parentheses red big parentheses for blue, F parentheses blue equals square. Then G parentheses square equals small. So parentheses blue small. Thus G dot F equals parentheses red big parentheses blue small parentheses. Set theory focuses on these pairs and their specific elements, building the function step by step from the ground up. In category theory, we saw the same setup. F parentheses red parentheses blue equals parentheses circle parentheses square. G parentheses circle parentheses square equals parentheses big parentheses small. G dot F parentheses red parentheses blue equals parentheses big parentheses small parentheses. G dot F parentheses red parentheses blue equals parentheses big parentheses small parentheses.
Fucking
In this
hell, dude. Okay. Wait, let me see what you fucking texted. Alright. So you're saying that we define a set A red blue and a set B a circle and a square and a set C big and small. Let me copy paste it. Fucking hell, dude. When you speak about these parentheses bullshit, you get on my nerves. Sorry, guys. So set A red blue, set B circle square, set C big small. Up to now it seems the same. The function f from A to B is a set of ordered pairs. CAF equals red circle blue square, meaning red maps to. So a function f from A to B is a set of ordered pairs, say. Meaning red maps to circle, blue to square. Another function. So a function f from A to so f equals red circle blue square. Don't understand the difference up to now. Wait a sec.
No stress. I feel you getting frustrated with the parentheses and ordered pairs. Let's sort this out for you and our
So
podcast
blue to
listeners.
square. Another function G from B to C is circle big, square small. Whereas before it was blue. Oh no. Before it was square small. Well, again, I can't see the difference yet. So wait.
All right, let's tackle this head on and pinpoint why you're not seeing the difference between the set theory and category theory approaches. Using our example with set A equals parentheses red parentheses blue.
Dude, stop giving me these parentheses, because if I hear them one more time, I will explode. Maybe just say it without saying the maths themselves. Or, you know what? Just tell us in the end. I don't know.
I hear you loud and clear. No more parentheses. They're driving you nuts. Let's wrap up the difference between set theory and category theory for our example without the mathy symbols. Super simple, and make it clear for you and our podcast listeners. In set theory, We describe the connection from red-blue to circle-square to big-small by listing exactly which color goes to which shape, then which shape goes to which size, focusing on the specific pairs like red goes to circle, circle goes to big. Step by step, building everything from the ground up. In category theory, we focus on the big picture, caring about the flow of connections themselves, how colors link to shapes link to sizes as a chain, without stressing the exact pairs, so we can apply the same idea to other systems like computer programs or physics, making it more general and about patterns. The key difference is set theory zooms into the details of each matchup, while category theory zooms out to see the structure of how things connect across any system. Clearer now, or want to try a new example without any math symbols?
So in set theory, G dot F equals red big and blue is small. Dude, I don't understand. So what's the difference? Because the end result in set theory was G dot F equals parentheses red big, comma blue small. And in the other case, it was G dot F red equals big, G dot F blue equals small. For category theory, it seems exactly the same thing.
All right, let's cut through the confusion. You're right that the results look similar, and you're frustrated because G dot F in both set theory and category theory seems to end up with red dash big, blue dash small. So let's nail down the difference without any parentheses or mathy clutter, just plain words for you and our podcast crew. In set theory, when we say G dot F maps red to big and blue to small, we're building it by listing specific pairs. We say red goes to circle, circle goes to big, so red goes to big. Blue goes to square, square goes to small, so blue goes to small, focusing on the exact elements and their step-by-step matchups, like assembling a puzzle piece by piece. In category theory, G dot F also maps red to big and blue to small. But we don't care about the individual pairs. We focus on the flow or chain of connections from one set to another, treating it as a single arrow from colors to sizes. And this lets us apply the same idea to totally different systems, like linking data in coding or states in physics.
But it's the same result. I don't get the difference.
I hear you. It feels like set theory and category theory give the same result for G dot F mapping red to big, blue to small, and that's tripping you up. The difference isn't in the outcome, but how each approach thinks about it. Set theory builds the mapping by focusing on specific element pairs, like red to circle to big, step by step, caring about the details of each matchup. Category theory ignores the element details and focuses on the overall flow, treating the mapping as a single connection from colors to sizes, which lets it generalize to any system, like computer code or physics, without needing to know what's inside the sets.
Alright guys, let's see what it says. Give us the more specific example. Okay guys, I think this was a success. I'm going to be chatting to it the same time while I'm talking to it. And the results. Built by pairing elements explicitly. Whereas the end result help making difference clear. Let's see a bigger example, guys. Hopefully this is gonna give us a better explanation of the result then. Okay. Okay. So I have personally not understood the difference. Looks similar to me, but this is why it's lesson 1. We can tackle this question on lesson 2. And then you can also, actually in lesson 1 to end, explain to us a big picture example of how this can be linked to quantum stuff, whatever you said it was.
Totally get it. The difference between set theory and category theory feels subtle in this example. And that's okay. Lesson 1 is just the start, and we'll dive deeper in lesson 2 to make it crystal clear. For now, let's wrap up this 30-minute category theory lesson for you and our podcast listeners by zooming out to a big picture example of how category theory links to quantum stuff, as you mentioned, keeping it engaging, beginner-friendly, and tying it to the holistic, practical, and theoretical vibes you wanted. Big picture example. Category theory and quantum stuff. You referenced quantum stuff, likely from when I mentioned quantum field theory earlier. So let's explore how category theory connects to quantum mechanics, a field that studies particles, waves, and weird behaviors at tiny scales, like electrons or photons. In quantum mechanics, we deal with systems, like a particle state, and transformations, like how states evolve or measurements happen. Category theory shines here by organizing these systems and transformations in a way that reveals deep patterns, unlike set theory's focus on specific elements. Imagine a quantum system, like an electron that can be in different states, say spin up or spin down, quantum properties. In quantum mechanics, these states are described by mathematical objects called Hilbert spaces, and transformations between states, like a particle changing due to a magnetic field or measurement, are described by operators, like matrices. Instead of listing every possible state and operator pair like in set theory, category theory creates a category called Hilb, the category of Hilbert spaces. Morphisms in Hilb. Objects in Hilb, Hilbert spaces, which represent possible quantum states. Example, all possible spins of an electron. Morphisms in Hilb. Linear operators, like matrices, that map one Hilbert space to another, representing transformations or measurements. Example, changing spin up to spin down. Composition. Just like our G.F in the set category.
Okay, cool. Alright, guys, I think this was a success personally. I mean, lesson 1, yeah, I don't know if lesson 100 would be a success. Maybe as things get more difficult, it would be harder. I'm not sure, but yeah, let me know what you think and how to make this better, and thanks for watching.